A lattice polygon looks like it should need lengths and angles to measure its area. Pick's theorem says something stranger. Just count the dots. For a polygon whose vertices sit on grid points, the area is the number of interior lattice points, plus half the number on the boundary, minus 1. In this example, there are 11 green interior points and 11 yellow boundary points. So the formula gives 11 plus 11 halves minus 1, which is 15 and a half. The rest of the video is about why this always works. The proof has 3 moves. Prove the formula for the smallest lattice triangles, cut every polygon into those triangles, then count the resulting graph. A fundamental triangle is a lattice triangle with no lattice points except its 3 vertices, none inside and none in the middle of an edge. For such a triangle, Pick's right-hand side would be 0 plus 3 halves minus 1, or 1/2. So we must prove, without using Pick's theorem, that its area really is 1/2. Move one vertex to the origin. Write the other 2 vertices as lattice vectors u and v. The triangle's area is half of the absolute determinant of u and v. Call that determinant d since u and v have integer coordinates. D is a positive integer. The goal is to show that a fundamental triangle forces d to equal 1. Suppose instead that d is bigger than 1. Now we use a piece of modular arithmetic, not Pick's theorem and not any area counting rule. Look at the map that sends a pair of residues r and s to ru plus sv. Taken modulo d, its determinant is d, which is 0 modulo d, so this map has a non-zero kernel. That means there are integers r and s, not both 0 modulo d, with ru plus sv divisible by d coordinate by coordinate. Divide by d, the point P equals r over d times u plus s over d times v, and P is an actual lattice point. Because r and s can be chosen between 0 and d minus 1, P lies inside the parallelogram spanned by u and v. If r plus s is at most d, then the 2 coefficients of u and v add to at most 1, so P lies in the original triangle. If r plus s is bigger than d, rotate P halfway around the parallelogram by taking q equals u plus v minus p. This q is also a lattice point. The coefficients of q are 1 minus r over d and 1 minus s over d. They are positive, and because r plus s is bigger than d, their sum is less than 1. So q lies in the original triangle. Either way, the original triangle contains a lattice point besides its 3 vertices. That contradicts being fundamental. Therefore, d cannot be bigger than 1. Since d is a positive integer and d is not bigger than 1, d equals 1. The area of every fundamental triangle is therefore 1/2. Now return to a general lattice polygon. Insert every lattice point inside or on the boundary as a vertex and triangulate without crossing edges. After this, no triangle in the dissection can hide another lattice point. If it did, that point would already have been inserted as a vertex. So every small triangle is fundamental. Let f be the number of small triangles. Each has area 1/2, so the polygon's total area is f over 2. Now view the dissection as a planar graph. If v is the number of vertices and e is the number of edges, Euler's formula for a polygonal disk says v minus e plus f equals 1. Count triangle sides. Each of the f triangles has 3 sides. Interior edges are counted twice and boundary edges once. Because the boundary has been subdivided at every boundary lattice point, the number of boundary edges is exactly b, the number of boundary lattice points. So 3f equals 2e minus b together with Euler's formula. This will determine f. From Euler, E equals v plus f minus 1. Substitute that into the edge count, simplify, and get f equals 2v minus b minus 2. The vertices are exactly the I interior lattice points plus the b boundary lattice points, so v equals I plus b. Therefore, f equals 2I plus b minus 2. Since area equals f over 2, the area is I plus b over 2 minus 1. That is Pick's theorem. The continuous area was forced by a discrete structure, fundamental half-area triangles, Euler's formula, and a final count of dots.